Okay, so let's see some questions related to this topic. The first question is, how does the force of gravitation between the two objects change when the distance between them is reduced to half? So the question says that there are two objects which have some gravitational force between them. So what will happen to that gravitational force if the distance become half? If the distance goes half. So the question number 1, see, let us say these are the two objects with the mass m1 and m2, and this is the distance between them, let us say r. So the force between them at this point of time would be F is equals to g times m1 m2 upon r square. Okay. Now if I make this distance half, okay, if I make this distance half like this is m1 and let us say this is m2, and the distance between them becomes r by 2, okay, then what would be the force between them? That would be F times g into F is equals to g times m1 into m2 upon the radius by 2, okay, square. So r by 2, the square of r by 2. So we can see, I can write this particular expression as, I can take this r square, okay, and this will become 4 at the denominator, it will go up, so it will become 4 times of g m1 m2 upon r square, like this. You can see g m1 m2 upon r square, this is what? This is equals to this one, this is let us say f1. So what you will get from here, you will get that f1 is equals to 4 times of f. So what is the conclusion that we can draw? I am not changing the mass of the objects, I am simply reducing the distance between them to half. So the distance become half, the force will become 4 times, okay, because the force is inversely proportional to the square of the distance. This is what we have learned in the universal law of gravitation. So we can see that when distance is halved, the force will become 4 times, okay, as the distance goes half, the force will become 4 times. So this is question number 1. Now let's see the second one. The question number 2 says, gravitational force acts on all objects in proportion to their masses, okay. Why then a heavy object does not fall faster than a lighter object? So question says that since the gravitational force, it is dependent on the masses, we can see it has the expression of mass in its formula, then why it is happening that heavy objects do not fall faster compared to the lighter objects? So we have learned, we have understood a concept regarding this, that there was a philosopher who tried to prove that when the two objects fall from or having a free fall, when two objects having a free fall, the velocity with which they are traveling, the speed with which they are falling on the ground is independent of their masses, okay. We have understood this concept. Now here we can see that it simply says that force is dependent on the mass, we can see m1 m2, but why it is like the velocity of the heavy object should be more, but it is not, okay, and lighter objects should fall slowly, but it is not. A heavier and a lighter objects both will fall with the same speed. For example, if I have an iron ball and if I have a wooden ball, if I throw them, if I drop them like this, what will happen? Both of them will fall simultaneously on the ground, okay. This is happening because if we see any object, let us say this is the object with mass m which is falling on the ground. I am talking about the free fall, okay, I am talking about the objects with free fall. So what you will understand, the force with which the acceleration with which this object is falling is g. So what we can see, the velocity of the object will depend on g. And what is the expression for g? We have learned this expression. The expression for g is basically g times mass of earth upon radius of earth. This is what we have learned. Now can you see, is there the mass of object is making a change? Does the mass of object is basically affecting the value of gravitational acceleration? No, we can see that g is not affected by the mass of this object. G depends only on the mass of earth, radius of earth and gravitational constant, the universal gravitational constant. So that's why here we will write heavy objects do not fall faster because the acceleration due to gravity is unaffected by the mass of object. Okay, the acceleration due to gravity is unaffected by the mass of object. I am talking about this object, its mass is not affecting the acceleration due to gravity, so that's why its velocity will do not have any effect because of its mass. Okay, so acceleration due to gravity is unaffected by the mass of object, and that's why we can say that both the objects, or heavier and a lighter object, or any object will fall with the same speed or at the same time as the other objects are falling. Okay, so this is how we can answer the question number 2. Now moving to the third one, it says what is the magnitude of a gravitational force between the earth and a 1 kg object on its surface. So there is an object which is kept on the surface of the earth, then what is the value, or what is the magnitude of the gravitational force that is acting on that object. Okay, so we know that if I consider this as the earth and this is the object kept on the earth, this is the object with m equals to 1 kg, this is the mass of earth me, and this is the radius of earth re. So what we can see here, the expression for the gravitational force will be F is equals to g times m1 into me upon re square. Okay, g m1 m2 upon r square, this is the expression. I am considering the two masses as one is the object and another is the earth. So we have the radius of earth, we have learned this concept earlier. Now the value of g, we can write all the values. The value of g is given as 6.7 into 10 to the power minus 11 into mass of object is 1 into the mass of earth is 6 into 10 to the power 24 upon the radius of earth is 6.4 into 10 to the power 6 and square of this. Okay, so we can write it as 6.7 into 6 upon 6.4 and into, this is 10 to the power minus 11 into 10 to the power 24 into 10 to the power minus 12. Okay, this will become 10 to the power 12 and we will shift this. Okay, so it will become 10 to the power minus 12. Now when you solve this expression, you will simply get 9.8 newtons. The force between a 1 kg object which is kept on the earth or on the earth's surface is experiencing a gravitational force of 9.8 newtons. Okay, so this is the third question. Now the fourth one, the earth and the moon are attracted to each other by the gravitational force. Okay, does the earth attract the moon with a force that is greater or smaller or the same as the force with which moon attracts the earth? Then why? Okay, it says that since earth and moon both are attracting each other towards them, so which object is attracting other object with greater force compared to the other object? Okay, if I compare the two objects, earth and moon, so the question is asking that does the earth will attract moon with a greater force or a lesser force as compared to the force applied by the moon on the earth. Okay, so we can see, we can simply answer this question in a way that as per universal law of gravitation, all objects attract each other with the force equal to G times m1 m2 upon r square. This is what is given. Okay. So what we can see, if this is the earth and if this is the moon, so earth will attract the moon towards itself with a force F and moon will attract earth towards itself with a force F. Now we can see, let us say this is F1 and this is F2. So we can see earth is attracting the moon with a force F1. This F1 will be equals to G times mass of earth, mass of moon upon distance between them is, let us say, r square. Here I can see the moon is attracting earth with a force F2, which is D times mass of moon, mass of earth upon the distance between them r square. This is what we can see. Okay. We can see that both these forces are exactly equal. Okay. Because ultimately the force is dependent on the distance between the objects and the product of their masses. I am simply multiplying the two masses. So that's why F1 will be equals to F2. Okay, that's why F1 has to be equal to F2. Okay, so this is the question number 4. Okay, so the next question is, if the moon attracts the earth, then why does the earth not move towards the moon? See, question says that earth is, we know that earth is attracting everything around it, and similarly the moon is also doing the same. But the question arises that when we throw a ball on the earth, okay, if we throw a ball up from the earth, that ball will get attracted towards the earth and again come to the surface, okay, again rebounds back. So why does it like that if earth is attracting the moon towards itself and similarly the moon is also attracting to earth towards itself, then why does the earth is not moving towards the moon? Why we are not moving towards the moon, or why we are not moving towards any other object? Okay. For example, if I throw a ball, the ball will rebound back on the earth, but why does not earth move towards the ball? Why it is happening? So this is a reasoning based question. For that we have to understand a simple concept. See, this is the earth and this is the moon. We can see that both of them are attracting each other with a force equals to G times mass of earth into mass of moon upon r square. This is the force. But the important point here to note is that the mass of earth is much larger than the mass of moon. So even if the moon is attracting the earth towards itself, what is happening? Earth is not moving towards the moon. The reason is simple, that there would be very less acceleration. Okay, the earth is not moving towards moon because the acceleration would be very less. Now why the acceleration is less? Because the mass of earth is huge compared to the mass of moon. So try to understand, force is basically mass into acceleration. Okay, so it means acceleration is equals to force upon mass. Now we can see that if the mass is more, the acceleration would be less. If the mass is less, the acceleration would be more. So here, because of this reason, I can say that acceleration of earth is much lesser compared to the acceleration of moon. Okay, this is the reason why the moon is revolving around the earth but not the earth is revolving around the moon. Okay, and because of the same reason, earth is revolving around the sun and sun is not revolving around the earth. Okay, this is the simple reason. So this is the question number 5. Now the next question, what happens to the force between the two objects if the mass of one object is doubled? So this is the question number 5. Now moving to the question number 6. It says that what will happen if the force, what will happen to the force between the two objects if the mass of one object is doubled. So this is again a reasoning based question. Let us say this is m1 mass, this is m2 mass, there is the distance between them as r. So at this point of time, these are the two objects with a distance r between them. The force of attraction, as per the universal law of gravitation, we can see that force of attraction F is basically equals to g times m1 m2 by r square. Now what will happen if I double any one of the mass? Let us say I double this m2 mass. Let's say this is my m1 and this becomes my m2. Just the double, and the distance between them remains r. So the force will become g times m1 into 2m2 upon r square. Now you can write this as 2 times of g m1 m2 upon r square. Okay, I can take 2 outside. Now compare these two expressions, this one and this one. You will find that g times m1 m2 by r square is common here and here. So I can replace this expression with this one and I will get 2 times of f. I will get 2 times of f. So what will happen if the mass is doubled? Okay, the force, you can see it is 2f, it means the force is doubled. The force is doubled. Okay. Then in the second part it says the distance between the two objects is doubled and tripled. So one, the distance is getting doubled, and another thing, the distance is getting tripled. So we are saying that force between the two objects is proportional to the product of their masses, okay, and force is inversely proportional to the distance between them. So what we can see, if r becomes 2r, okay, if the distance becomes 4 times, okay, sorry, the distance become double, distance become 2 times. So what we can see, if r becomes 2r, then force will be, we can see that it is proportional to 1 upon r. So force will be proportional to 1 upon 2r square, and this would be equals to 1 upon 4r square, which is equals to f upon 4. Okay. So the distance become doubles, the force will become 1/4. Okay, force will become 1/4. Force will become 1/4. Now similarly, if the distance is tripled, what will happen? The distance will triple, so f will be proportional to 1 upon 3 times r to the power 2. This will become 1 upon 9 r square, and here again we can see f upon 9. So what is happening? When the distance was r, the force is f. Now when the distance become 3r, the force become f by 9. So I can say the distance become 1/9. Okay, the distance become 1/9 of the the force will become 1/9 of the force when the distance was r. Then the third part, masses of both the objects are doubled. Now again we can see the force is proportional to the product of the masses. So I can say that if we can see that m is proportional to m1 and m2. Now if m1 becomes 2m and m2 becomes 2m, the force will become 2m1 and 2m2. So we can see f will be proportional to 2 2s are 4 into m1 and m2. So we can see what is m1 and m2. This is f, this is the, let us say f1, this is f1. So we can see the f1 will become 4 times of f, because the other things are constant. So we can see that when the masses of both the objects is doubled, the force will become 4 times. Okay, the force will become 4 times when the masses of both the objects is doubled. Okay, so this was question number 6. Okay, so please note this. Okay, let's solve the question number 7 now. The question number 7 says, Amit buys few grams of gold at the poles as per the instruction of one of his friends. he hands over the same when he meets him at the equator, will the friend agree with the weight of the gold bought? If not, then why? So the question says that Amit is standing at the pole. Okay, Amit was asked by a friend to buy the gold when he was standing at the pole. Now try to understand this. Is a very interesting, a very logical, a very conceptual question we have here. So question number 7. See, we are talking about the earth, and in actual we know that earth is bulging from at the equator, and it's a bit pressed at the poles. So this is the poles, okay, and this is the equator. Now Amit was standing at the pole and he bought some gold at this point. Okay, Amit was standing here and he bought some gold at this point. Let us say he bought the gold of mass m at this point, and if the mass of the gold is m, then what would be the weight of this gold? Okay, so weight of gold at poles or at pole. Now the important concept here, we have learned that there is a difference in the acceleration due to gravity at poles compared to the equator. We have learned this concept. So what I mean to say, here I have to consider that situation that at poles the acceleration due to gravity is more. Okay, let's say Gp is the acceleration due to gravity, and at the equator, let's say this is Ge, so acceleration due to gravity at equator is less. Okay, why? Because the poles are closer to the center of the earth compared to the equator. Okay, equator is something, it's like earth is not a perfect sphere, it's pressed. Okay, it's pressed at the poles and it is bulging out at the equator. So that's why we will say that if Amit buys some gold at this point of mass m, the weight of gold at this point would be mass into acceleration due to gravity, and acceleration due to gravity we have considered it as Gp. Okay, now when the Amit bought this gold and on the equator, will the mass of this gold going to change? No, the mass will remain m. But what about the weight? Weight of the gold at equator will become mass of gold, that will be m, and the acceleration due to gravity at the equator, Ge. So what we can see, since Ge is less than Gp, the gravitational acceleration at equator is less than compared to the gravitational acceleration at poles. So we will say, since Ge is less than Gp, so weight of gold at equator would be less than weight of gold at pole. Okay, the same gold which has the mass m, its mass is not getting changed, but what will happen? This acceleration due to gravity is getting changed, and that's why you will find that the weight of gold, okay, the weight of gold will change at these 2 points, that is at the equator and the pole. Okay, this weight will definitely going to change. So the question says that since the weight is, will the friend agree with the weight of the gold bought? No, we will say the friend of Amit will not agree with the weight of the gold that Amit bought. The reason is simple, that weight of gold seems to be, okay, different, or weight of gold seems to be lesser compared to the weight of gold when he bought gold at the equator. Okay, this is what will going to happen. So this was question number 7. Now moving to the next one. Question number 8, it says, gravitational force on the surface of the moon is only 1/6 as strong as the gravitational force on the earth. Then what is the weight in newtons of a 10 kg object on the moon and on the earth? Okay, so the question number 8, it says, there is an object with a mass 10 kg. Okay, when it is on the earth, this is the earth and this is the moon. when this object is kept on the earth, then what would be its weight, and when this is kept on the moon, then what would be its weight. So we can see the weight is equals to mass into acceleration due to gravity. We can see that acceleration due to gravity on earth is g and acceleration due to gravity on moon is g upon 6. Okay, it's g upon 6. For practical purposes, let us consider that g is 10 meters per second square. So we can see weight of this object on earth will be mass is 10 into gravitational forces, gravitational acceleration is 10 newtons, okay, that is 100 newtons. And if we go on the moon, so the weight of the same object on the moon, its mass will remain 10 into acceleration due to gravity will become 10 upon 6, so its weight will become 100 upon 6 newtons. Okay, so what we have to find? So its weight on the earth is 100 newtons and weight on the moon is 100 by 6 newtons. It's simple because the acceleration due to gravity becomes 1/6, and we have learned that weight is basically mass into acceleration due to gravity. So that's why the weight will become 1/6. Now moving to the next one, a ball is thrown vertically upwards with a velocity of 49 meters per second. So what I am doing, I am basically throwing a ball like this. I am throwing a ball up with a velocity of 49 meters per second. So to imagine the situation, let us draw some simple diagram. Let us say this is the ground and this is a ball which is thrown upwards with a speed of 49 meters per second. Okay, we call this velocity as u, that is the initial velocity which we have learned in the chapter motion. Okay. Now when this ball is thrown, what you can see, when I am throwing a ball, the ball is moving under the influence of gravity only, and we have learned that when an object is moving under the influence of gravity, it is called a free fall. Okay, we call it as a free fall because when the ball is rising up, it will stop at some point and it will start falling down. Now when the ball is moving up, the acceleration due to gravity g would be downwards. When the ball is falling down, then also the acceleration due to gravity will be downwards. So we can see that when an object is going up, the acceleration and the velocity both are in opposite direction. G, for practical purposes, we will take g as 10 meters per second square. Okay, the acceleration due to gravity, we take g as 10 meters per second square. So what we have to calculate is the maximum height that this ball will going to achieve. Maximum height that this ball can achieve. So what we can see, when I throw the ball from this point, it will reach some height, and at that point of time, the maximum height, at the maximum height, this ball will have the velocity equals to 0 meters per second. Okay, the velocity of the ball at the maximum height, because when you throw a ball like this, what will happen? The ball will rise in the air and stop at some point, and after that it will start falling from that point. So it means the point at which the ball stops will be the maximum height that it can achieve. So you can see this is v, this is u, and this is the acceleration due to gravity. So can we calculate what exactly is the distance that this ball has travelled? Yes, we can calculate it by using the equations. We know an equation, that is v square minus u square is equals to, now since we can see that g and this initial velocity u, they are in opposite direction. Okay, you can see the ball is moving up, but the acceleration due to gravity is downwards, so this g will become negative of g. I can write this as 2 minus g into h. Okay, we have seen that in case of free fall, how the formula, how the equations of motion will change, and this is like we have to change it. So now by substituting the value, this is the 0 square minus 49 square is equals to minus into 2 into g is 10 into h. Okay, so you can solve this 2 and 2 will get cancelled. This is 49 into 49 upon 20, this is h. This is in meters. This much distance, this much height the ball can achieve. Okay. Second thing it takes, the total time it takes to return to the surface. Now it is asking us that if the ball is achieving this height, okay, I am saying that ball is achieving this height, then how much time will it take to reach this height and come back to the ground? So I will say that once it reaches the height, the time taken to go up will be equal to time taken to go down. Okay. So what we will say that time to go up will be equals to time to come down. Okay, and therefore total time would be time to go up plus time to go down. This would be the total time. Now how will you calculate the time? We can use the equation V is equals to U plus AT. Here V will become 0, is equals to U is 49. Now A, again we have seen acceleration due to gravity, it is downward, and while the object is moving upwards, its velocity is upwards. So minus G, it is 10 into T. So T comes out to be 4.9 seconds. Okay. Now the object is moving to the height of this much in 4.9 seconds. It will also come down in with the same in the same time. So the total time will be equals to 4.9 plus 4.9, that is 9.8 seconds. The object will take total time equals to 9.8 seconds to reach the ground. Okay. Sorry, this was the question number 9. Okay, so you note this and then we will continue. Okay, let's see the 10th question. It says a stone is thrown vertically upwards with an initial velocity of 40 meters per second, taking g equals to 10 meters per second square. Find the maximum height reached by the stone and what is the net displacement and total distance covered by the stone. So the question says that the stone is basically thrown from the ground with the speed of 40 meters per second. Okay. So this question is just similar to what we have done recently. So this is the stone. We are throwing this stone with the speed of 40 meters per second. Okay. Now when the stone is rising in the air, I will say that acceleration due to gravity g will be 10 meters per second square in the downward direction. Okay. So the question is, find the maximum height it can reach. So as we have learned earlier, it is thrown from the ground. This is the ground. So the maximum height it can reach is a point where its velocity will become 0 meters per second, because it will stop in the air at some point. So now we can see we have 40 as u initial velocity, v as the final velocity, and this is the acceleration. So we can apply v square minus u square is equals to 2as. Here we have v as 0 square minus u square. In place of u I can write square of 40 is equals to, now with 2 and minus g into s. S means the distance that the object is traveling. Okay, I can replace this s by h. This is the height that the stone can achieve. So I can write here h. Okay, because this is the formula that we have derived earlier. We are using it here. So you can see that this g will become 10. So 40 into 40 upon 2 times of 10, this will become h, and you can see this will get cancelled 2 times. So h will come out to be 80 meters. Okay, so the object is traveling 80 meters till this point. Okay, and then it will start dropping from the same point and will reach the same point. Okay, for example, if I am throwing the stone from point A, it will reach point B, then from after reaching the point V, it will stop and it will start coming down. Okay, it will start falling. So here is the condition that we have learned earlier, that when an object is thrown upward, okay, when it is falling down, when an object is falling under the influence of gravity, we call it as a free fall, and the motion of that object would be a straight line. Okay, so let me write the statement what I am saying. During free fall, the motion of object is a straight line. Okay, so it means if I throw an object from point A, it will reach point B and it will start falling from the same point, and it will again reach point A. So if I talk about the net distance that the object has travelled, net distance is equals to AB plus BA. Okay, AB plus BA, AB is equals to 80, recently we have calculated, so BA will also be 80. The height that it has achieved, the maximum height, it will start falling from that point to the ground, so it is 80 plus 80 equals to 160 meters. But what about the displacement if I say? As we can see, I am throwing an object in a straight line, it is coming down in a straight line, so after complete motion of the object, it will again be at the same point from where it started. Okay, so that's why net displacement will be equals to 0 meters. The net displacement would be 0 because it is starting its motion from point A, it reaches point B and again fall to the point A. Okay, so net displacement is 0. So this is how you can solve these questions. Okay, so you can note this.